For today's segment, we want to now also discuss the biological effects of ionizing radiation. And exactly what are these biological effects? We have all a fairly good understanding that X-rays are not very healthy. As we've discussed, we need to put on sunscreen to minimize ionizing radiation. And it is actually exactly those ionizing effects that are at the center stage here. The ionizing effects are pretty much instantaneous. The minute the photon hits our molecule, it produces an ionizing effect, produces a molecule with a charge, it's ionized. This happens today and now. This can produce free radicals. This can break chemical bonds. This can produce new chemical bonds or cross-linkage between macromolecules, for example in the eye. Or it can damage molecules that regulate vital processes, for example, certain proteins, RNA, and DNA. So what we have is the X-ray that impacts on our cell. It, for example, in this graphic here, it breaks the DNA structure. This happens instantaneously. It is now. If you're exposed to the X-ray, this happens now. However, and this is one of the difficulties here, is that the biological effects are delayed. In the eye, we can have cataract formation. That's cross-linkage between macromolecules. That's cataract. This can happen months later or years later. And if the cell is losing its ability to autoregulate, this can produce cancer. This can happen years later or decades later. And this is the difficulty in managing the X-rays. We cannot immediately see the effect. We cannot immediately judge it. And it is detached from the original event. So, the dysregulation of a cell, where it loses its autoregulation, it starts to grow uncontrolled, that's cancer, develops into tumor, that happens months to years later. Sometimes it's relatively short, and here's an example of a person who underwent actually an angiogram in a CT scanner. So, and you can see here on the hair cells on the surface, they were exposed to very high radiation in this case, and this created radiation damage in the skin of this person who lost the ability to grow hair. This was most likely temporary, but it is an effect that happened in the few months after the scan. Now, what complicates the assessment of biological effects is that not all tissues are equally sensitive to radiation. If you have a tissue that has a rapid cell proliferation that divides the cells rapidly, then it is the sensitivity of that tissue is proportional to the rate of cell proliferation, so it is high. So if you have a tissue that has a lot of cell proliferation, then it is more sensitive to radiation. On the other hand, if the tissue is highly differentiated, then it is less sensitive to radiation. And this is a very practical consideration, that actually we have a relatively high rate of cell proliferation in fetuses compared to old age, where our cells just don't divide as fast. So a young person is much more susceptible to the biological effects of radiation than an older person, where it is less important. So the damage that is created is less of a concern when you're increased in age. So this has considerations on exposure to radiation, but also in, for example, radiation cleanup, that is as in the cases of Fukushima, where they have used for the first firefighters that came to work on the cleanup of the site, they preferably selected people that were of older age than the younger firefighters, exactly for that reason. Another thing to consider is at old age, even if you develop a cancer due to radiation exposure, the cancers tend to grow slower at old age, and so there's a higher probability that you might die of a heart attack rather than of the cancer produced by the X-ray exposure. So if you look at sensitivity upwards, then the nervous system is not very sensitive. The muscle is a bit more sensitive. Then we have bone and teeth. We have the skin. We have the reproductive organ, and finally the blood-forming organs, which are the most sensitive to radiation. So, one process is the production of radicals, that is, compounds with unpaired valence electrons, and reactive oxygen species, such as we have two OHs that produce hydrogen peroxide. Radicals and reactive oxygen species are produced by processes that are naturally occurring in the body. And one such process is oxygen consumption. It's the mitochondria that are responsible for that, and they are a powerhouse of radical formation and reactive oxygen species production. So it happens naturally in our body. And this is where the good news are. Our body has to have, in order to survive these processes, has to have developed defense mechanisms against the production of radicals and reactive oxygen species. And this is what we are going to discuss next. So, how does the tissue defend itself against radiation damage? And we can distinguish basically two processes. We have the X-ray that produces an ionizing event. This ionizing event happens directly on the molecule of interest, so that would be the direct effect. We have ionizing event directly on the DNA here in this example, and that's direct damage. We can also have an ionizing event in another molecule. This produces then water and an electron. This produces then H3O plus and a free electron, and through these reactive oxygen species we have the indirect effect through a chemical reaction. If we look at DNA, which is what we are mainly concerned with, the DNA is constantly subjected to processes that menace, that threaten its integrity. We have alkylating agents, we have oxidizing agents, we have replication errors, we have aging, we have radiation, natural radiation, we have diseases. And so the cells, our cells, have developed mechanisms to provide for repair of the DNA. So there are, to counter all these effects, there are repair mechanisms that exist. And now if we look at the healing of the tissue that's been exposed to X-ray, we are looking at essentially two fundamental ways. One is repair. In repair, the cells in the tissue are being replaced with a different cell type. Typically it's fibrosis. In this case, the organ is not returned to the original state. We take a liver cell, replace it with a fibrous cell. There is not a liver cell again in that tissue, or in the brain, for example. In radioresistant tissues, the tissues that are less likely to be damaged by radiation, such as muscle and brain, we can only do repair. This is the only mechanism that happens. So in the brain, a cell that is being damaged by X-rays is not being replaced by a cell of the same kind. The other process of healing that happens is regeneration. In this case, the cells that are damaged by the X-rays are replaced by the same type of cells. The organ is therefore returned to its original state. It still has the original, the proper cells in there, and the process of regeneration happens in tissues that are more sensitive to radiation, such as skin. Skin regrows, as we all know. We have all cut ourselves. It happens in the digestive system and bone marrow. These are the fundamental processes of interaction of X-rays with tissue, the damage, how it's done, but we still do not know how to relate this to quantities that we can measure for our imaging techniques. So the question is, how do we quantify the effects of ionizing radiation? And here the literature is, at first glance, quite confusing, because there are three terms of radiation dose that are being used. First, we have the absorbed dose. The absorbed dose is essentially very simple. It's the energy deposited by the radiation per unit mass of material. So it is essentially the energy per mass. It's joules per kilogram is the unit, and here the unit Gray was introduced, GY. That's the absorbed dose. So the absorbed dose here is given by the number of photons times their energy. Each photon carries a certain energy. If we have 1,000 photons of them, we deposit more energy per mass than if we have only 100 photons. So D is proportional to the photon energy times the number of photons. So in other words, the absorbed dose depends on the intensity of the incident X-ray and the duration of exposure. There is no per time here, it's per mass. The next term is the equivalent dose, H. And it is essentially equal to the absorbed dose, but then it's corrected for the possibility of the type of radiation that is being used to produce biological damage. Not all types of radioactivity produce the same kind of can produce damage to biological tissue. So mathematically, H is again is given by the absorbed dose, D times WR. This is a tissue weighting factor. Now the units to distinguish this are given in sievert. In SI units still is joule per kilogram because the tissue weighting factor is dimensionless. And the good news is for biomedical imaging, we have a tissue weighting factor of 1 for X-rays and beta particles. Those are the majority of ionizing radiation that is being used, primarily X-rays for our course. And it is 20 for alpha particles, but we are not considering imaging with alpha particles. So we do not consider that. So the good news is equivalent dose is equals to absorbed dose for biomedical imaging. That is the relationship that we have for the types of X-rays that we use. And finally, there is the third term, that's the effective dose. And this is essentially taking into account, once we have the equivalent dose of our radiation, in our case is equal to the absorbed dose, we have to correct this for the sensitivity of the tissue to the radiation. So we'll introduce here now a tissue weighting factor. And so the equivalent dose, it's given in sievert, is equals to the sum of the equivalent doses, H, here, for the given tissue. So how much is this tissue in sievert exposed to the radiation? And then we multiply it by a weighting factor, WT. We'll have to do it all over all the tissues to get the total equivalent dose. So we'll take this for all types of tissues, and here is a list of different tissues. The tissue weighting factor, WT, for different tissues. And actually you find for the gonads it's very high, for skin and bone surface it's very low. Then we have a number of organs where it's 0.05 and 0.12. Again, there are not huge differences, but there are differences in terms of the sensitivity of the tissue different tissues relative to the X-rays they're being exposed to.